Imagine you packed a suitcase, launched today in the fastest spacecraft humans have ever actually sent out of the solar system, and your descendants would still be traveling long after every country on Earth has changed names, every coastline has shifted, and every language you speak right now has evolved into something unrecognizable. That's not sci-fi. That's the math. Now here's the first mind-bender. The nearest star system to us is Alpha Centauri, and the closest star within it is Proxima Centauri. It's about 4.246 light-years away. And light-year is where people get tricked. It's not time. It's distance, about 40 trillion kilometers. So let's start with the most brutally honest baseline. How long would it take with what we have already done, not what we wish we could do? Voyager 1 is the classic benchmark because it's really leaving. It's moving at about 17 kilometers per second relative to the Sun. That's around 61,000 kilometers per hour. Sounds fast, until you realize the distance to Proxima Centauri is 40 trillion kilometers. Do the division and you get roughly 75,000 years. 75,000 years. Pattern interrupt. Agriculture is only about 12,000 years old. Voyager time to the nearest star is about 6 times the entire history of farming, cities, and written civilization combined. And that's just to arrive near the star's neighborhood. It doesn't include slowing down. Voyager can't brake. It would scream through the system and keep going. Now let's flip the perspective with a second gut punch. The fastest thing in the universe, light itself, still takes 4.246 years to get there. So even if you could teleport your spaceship to light speed, something physics does not allow for objects with mass, you'd still be waiting more than 4 years just for the trip to finish. And if you sent a radio message that said hello, you wouldn't get a reply until at least 8.5 years later, because the answer has to travel back. So why is this such a big deal? Because the problem isn't only distance. The real villain is energy. To go faster, you need huge changes in velocity, and space travel punishes you for that. Rocket fuel has mass. More fuel means more mass. More mass needs more fuel. That spiral is why chemical rockets get us to orbit and to the moon, but they don't casually push a ship to a meaningful fraction of light speed. The rocket equation is basically the universe saying, pay up. Now, people will argue in the comments, but we've made faster spacecraft than Voyager. Yes and no. The Parker Solar Probe has reached speeds around 190 kilometers per second at its closest approach to the Sun. That's the fastest any human-made object has ever moved. But here's the catch. Controversy time. Those headlines are slightly misleading for interstellar travel. Parker is borrowing speed by falling deep into the Sun's gravity well, like a skateboarder dropping into a half-pipe. It doesn't leave the solar system at 190 kilometers per second. Its job is to orbit the Sun, not escape to the stars. For escaping the solar system, Voyager 1 remains a realistic, we actually did it reference point. Okay, so what if we built something specifically to go fast? Let's talk speed targets, because this is where the numbers get spicy. If you could travel at 1% the speed of light, 0.01 c, that's about 3,000 kilometers per second. At that speed, the trip to Proxima Centauri is about 425 years, not counting time to accelerate and decelerate. That's not a weekend getaway. That's a civilization project. Multiple generations living and dying on the way, with no resupply, no rescue, and a ship that must function for centuries. If you could travel at 10% the speed of light, 0.1 c, now you're talking about roughly 42 to 43 years in transit, again not counting acceleration and braking. That's one human lifetime territory, which is why 0.1 c is the speed that makes people's eyes light up. But it's also where the engineering turns brutal. Shielding, power, propulsion, and reliability all become extreme. And at 20% the speed of light, 0.2 c, you're at about 21 years in cruise. This is why the Breakthrough Starshot initiative, announced in 2016, became so famous. It proposed sending gram-scale probes pushed by powerful Earth-based lasers to around 0.2 c. Not a crude ship. Tiny probes, Because mass is the enemy. Even that remains a concept with enormous challenges. Building and powering the laser array, aiming it, keeping the sail stable, and surviving interstellar dust impacts at relativistic speed. Now let's address something people hate hearing. Interstellar travel is not just make the engine stronger. It's make everything stronger. At high fractions of light speed, even a grain of dust becomes dangerous. The interstellar medium is thin, but at zero point 0.1 c, tiny particles hit with huge kinetic energy. That means shielding isn't optional. But shielding adds mass, and mass makes propulsion harder. See the trap? Then there's braking. Getting there is only half the problem. If you want to actually study a planet up close, you need to slow down. Carrying fuel to brake adds mass. Using something like a magnetic sail to push against interstellar plasma might help in theory, but it's not a solved, fielded technology. So here's the controversial question that keeps scientists up at night. Should we even be talking about sending humans at all? Because for the foreseeable future, probes beat people in every category: mass, life support, radiation protection, reliability requirements, and ethics. A human mission needs air, water recycling, food production, psychological health, medical care, and radiation shielding for decades. A probe needs power, instruments, and a transmitter. And the irony is, in some ways, we're already doing interstellar communication better than interstellar travel. Our radio and TV bubbles have been expanding at the speed of light for about a century. Those signals are faint and messy by the time they reach a few light years out, but the front edge is still racing outward. The first hello from Earth reached the Alpha Centauri region years ago. No reply, obviously, but that's a real, physical fact. Our presence is already detectable in principle, even if the signal is weak. Now, let's bring it home with a clean summary using real, grounded numbers. With our fastest proven interstellar-bound spacecraft speeds, reaching the nearest star takes on the order of 75,000 years. At 1% light speed, it's around 425 years. At 10% light speed, it's around 43 years. At 20% light speed, it's about 21 years. And light itself needs 4.246 years. So when you hear, "we'll go to another star," the most honest follow-up is, at what speed, with what propulsion, and are we trying to stop when we get there? Because the distance isn't just far. It's far in a way human brains did not evolve to intuit. It's so far that our normal sense of fast becomes basically useless. But here's the part that should spark curiosity, not despair. The story of spaceflight has always been a story of changing the meaning of impossible. Not with wishful thinking, by paying for it with physics, engineering, and time. Interstellar travel isn't blocked by one wall. It's blocked by a whole maze of walls. Energy, mass, shielding, braking, communication, and the simple requirement that a machine must keep working longer than most human institutions have ever lasted. If you want more videos that turn huge space questions into real numbers you can actually feel, follow for the next one. Because the next question gets even wilder. If we did send a probe, what would it even see when it arrived? And how would it send that data back across 4.2 light years? Now I want to know what you think. Would you rather humanity spend the next century aiming for a tiny laser-pushed probe to another star, or focus on building a ship meant to carry people? Even if it takes generations to arrive,